Welcome to Calculus 411. Tonight with us we have Megan Carr to help us with optimization problems. Tell me, Megan, what is optimization?
Optimization means finding the maximum and minimum values of a quantity, or finding when these maximum and minimums occur.
Now, how exactly would you use optimization in a real-life scenario?
You would use optimization in a real-life scenario, such as economics with finding the maximum profit or maximizing your space in a storage unit. Here are the following steps to help you solve these problems.
The first step is read the problem. The second step is draw a picture. The third step is to label all the variables given. The fourth step is to reread the problem. The fifth step is to decide if you're trying to find maximum or minimum and write the function. The sixth step is to use the relationship between the functions from the extra information of the problem and rewrite the function to be optimized in the terms of just one variable. Step 7 is to take the derivative of the function. Step 8 is to have the derivative, find the derivative, the first derivative, and set it equal to 0. Step 9 is to solve the variable for the equation f equals 0. The 10th step is find the second derivative. Step 11 is to check the zeros of the second derivative and find out if it is positive or negative. And if it is negative, it is concave down. If it is positive, it is concave up. And finally, if the variable was bounded in the range of the critical numbers, then the variable of the function of each critical point of interest, the relative maxima, if you are trying to find the relative maxima, the relative minimum, if you're trying to minimize, and at the endpoints of the range 0 to 100, you can decide the variables optimized of the function.
Geez, Megan, you make it seem so easy.
Because it is easy, let's take an example.
So you want to produce and design a box that is a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume?
Here's the image of the problem. Since we have a square base, both the width on this side and the width on this side will be the same, and we will label it x, and h will be labeled as the height. Our primary equation will be the volume of the box, which is v equals x squared times h. S equals the area of the base plus the area of the four sides. This is the surface area. This will be our second equation. S equals x squared plus 4xh equals 108. V equals x squared h is our primary equation, so we will solve for h. X squared plus 4xh equals 108. We subtract x squared from both sides and we divide by 4x. So h will be 108 minus x squared divided by 4x. So we plug that in for h into the equation. So x times the quantity 108 minus x squared divided by 4x. We will get 27x minus x cubed divided by 4. This is a derivative and we use the chain rule. The feasible domain is 0 is less than x, which is less than or equal to the square root of 108. This is the domain. The derivative is dv over dx equals 27 minus x squared divided by 4, and we set the equation equal to 0. 3x squared equals 108. We got 108 from multiplying by 4 to 27. So then we divided by 3 and took the square root, and x equals plus or minus 6. This is the critical number. To maximize the profit, the the dimensions must be 6 by 6 by 3 inches.
And this concludes our segment on optimization. Thank you for tuning in to Calculus 411. Next time, do better on your test.
So we don't have to do this again.
Love you, Miss Pete.